In this video, we are going to show how to derive the conditional variance of the OLS estimator. To do that, we're going to use the partialing out interpretation. So first, we're going to do a little review and show that the residuals in the partialing out interpretation only depends on all the x's. Then in the second part, we'll do the standard derivation of the conditional variance. So first, let's consider a simple model where we have the y's depends on the intercept, beta 0, plus a first variable x1, plus a second variable x2, and there is a residual ui. So remember, we do a two-step approach with a partialing out approach. And first we have to regress, for instance, xi2 on xi1. And we get a residual here. So we have estimates, alpha 0 hat, alpha 1 hat, and we use the estimated residual, ri hat 2. Now, ri2 hat is just xi2 minus alpha 0 hat minus alpha 1 hat xi1. Then alpha 1 hat is the standard formula for an OLS estimator in a simple regression. So it's just sum of xi1 minus x1 bar times xi2 minus x2 bar over, and here we regressed it on xi1, so at the bottom we have the sum of the xi1 minus x1 bar squared, and we see here it only depends on x. x1 and x2. For alpha 0, in a simple regression, remember that we just have x2 bar minus alpha 1 hat x1 bar. So again, the x2 bar and the x1 bar only depend on x, and alpha 1 also only depends on x, so alpha 0 just depends on x. So since the residual is just xi2 minus things that only depend on x, we can deduce that the residual ri2 only depends on the x's. So what I mean by that is, like, it doesn't depend on the residual ui or on yi, the dependent variable. So now we can go over the second part and use that to derive the variance of the OLS estimator. So remember that for an estimator, beta j, we just sum the product of the yi and the residual for the variable j, so ri j, over the sum of ri j hat square. So for the conditional variance, we use this formula. So we have the variance of the sum of yi's rij hat over sum of rij hat square, conditional on x. I'm going to expand the y here, and let's say we have a complicated model. So we will have something that looks like beta 0 plus beta 1 x1 plus etc. plus beta k xi k, and then plus a residual ui times the residual of the first regression rij hat and conditional next over the sum of the residual rij hat square. So here I'm going to distribute the residual rij hat, but only on two parts. I'm going to have this first part here, so that I'll keep between brackets, and I'll separate the ui. So it's going to look like this. Variance of the sum of beta 0 plus beta 1 xi1 plus etc. plus beta k xik times rij hat over the sum of rij hat square plus sum of the ui's rij hat over the sum of rij hat square. So remember, the variance of something that's constant plus a random variable is just the variance of this random variable. The constant doesn't change anything in the variance. If we go back here, since we conditioned on x and everything here depends only on x, remember that the ri hat depend only on the x's. We don't have any y, we don't have any ui, so this is constant. The only source of variability are the x's, and we conditioned on it. So since this is constant, we can just remove it, and we just have the sum of the ui rij hat over the sum of rij hat square conditional on x. So we simplified it a lot by just separating all the terms that depends only on x's and just keeping the part that depends on the ui. Now, the bottom part here in the variance is also constant in x, so remember, the variance of a constant times a random variable is just the constant squares times the variance. So we are going to do this here and take the sum of the rij squares, get them out, and we have to square this times the variance. Now we just have the sum of ui rij hat. Note that now the variance of a sum is the sum of the variance if xi's are independent from each other, are linearly independent. Here we have condition on the r's, so on the x's, so r is constant, and we have just the ui's that are variables, and we assume that they were independent. So here we have a sum of independent variables, so we can actually bring the variance inside the sum sign. So let me rewrite that. First I'll simplify the constant in the front. I will just have sum of 1, and 1 square is 1. Rij hat square, and the bottom is square. The whole sum is squared. Times the sum of the variance of the ui times Rij hat, conditional on x. So again, here in this expression, the Rij's are constant because we condition on x, so we can take them out of the variance and square them. So we have 1 over the sum of the Rij's squared and the whole sum squared times the sum of Rij hat squared, we take it out, we square it, times the variance of the ui, conditional on x. Now, we are going to use one of the assumptions. So we're going to use the 5th assumption of the multiple linear regression model, which is homoscedasticity. So this assumption says that the variance of the ui, conditional on x, is constant, and we'll call it sigma square. So we can replace this here, the variance of the ui, by sigma square. So we get variance of beta j, conditional on x, is equal to 1 over the sum of Rij hat square times the sum of Rij hat square times sigma square. Now, sigma squared is constant, it doesn't depend on I, so I can get it out of the sum, and I get sigma square times 1 over the sum of the Rij's hat squared times the sum of the Rij hat square. And we can see we have the same at the top and the bottom here, except that at the bottom we have a square. So we can divide it, and we end up with times 1 over sum of Rij hat, and we just have one square here. The second square cancels out with the top part. So this is the result. Variance of beta j hat, conditional on x, is the variance of the ui's. So the more variance we have in the error means on average the larger the error, the less accurate is our beta j. And at the bottom we have sum of Rij hat squares, and this is the variance of the xj that is linearly independent from the other x's. So basically it's the variability in the xj that we can't explain, or we can't correlate with the other x's. So what it means if we have two x's, let's say x1 and x2, and they tend to move together, we don't have much more information looking at x2 that we have looking at x1. So on the contrary, if x1 and x2 don't move together, then the residual here will be large, and we'll have a lot more information by adding x2 to our models than just by looking at x1. Thank you very much, and see you next week.